Thank you very much, Professor Neff, and welcome everybody to my presentation. The title was already mentioned, and the contents of my presentation are: first, I will give you, of course, a short introduction to the topic. Then I will explain our model for twisted polymer cords to you. In the next step, I will explain our extended periodic boundary conditions in order to create shell-like representative volume elements. And this is the point where the connection of our work is to this conference. And of course, I show you some results for uniaxial and the cross-layer reinforced composites. And finally, I will close my presentation with a short summary and a brief outlook. Here, cord-reinforced rubber structures have numerous industrial applications due to their special mechanical properties. So these composites are characterized by very high tensile stiffness in cord direction and a very high compliance under shearing and bending. And in this picture, you can see three typical applications with an air spring, a tire, and a driving belt. The picture to the right shows us the cross-section of an air spring bellow, where you can see the rubber matrix and the cord reinforcement. The picture below shows a longitudinal section of the cord, where you can see that the cord itself consists of at least two twisted yarns. And each yarn is itself a complex structure or a complex twisted structure of filaments. So a cord itself is not a monolithic body. However, it has a very complex setup, and the setup of the cord mainly influences the properties of the cord and, of course, the composite. The aim of our research project is to develop efficient and application-oriented simulation methods for cord rubber composites within the commercial finite element programs like Abacus or MARC, for example. And as a first assumption or as a first approach, one could say, okay, let's analyze or let's use a cyclic symmetric model of the rolling lobe of such an air spring. And this model is or has very good properties because it gives us very good results under realistic loading conditions of the air spring. But if we are interested in an efficient optimization of the cord rubber composite, we have to decrease the computational effort, but without losing information about the loading conditions of our component to be as realistic as possible. And so we want to focus on small details, so-called representative volume elements, and we want to use extended periodic boundary conditions to apply, for example, bending loads to such composites. Of course, we are not the first one who tried to analyze cord rubber composites with representative volume elements. So Pollai proposed a model of a cross-layer reinforced composite where he used a very easy approach for the cord. He used a cylindrical cord. And this is very easy to mesh, and he avoids the problems related to the cord geometry during the meshing process. But unfortunately, these models have only a few set of geometry parameters available. So there is no information about the period length of the cord, for example. And this is very often tried to compensate by using complex material models. And we want to follow another approach. We want to use a simple structured mesh of the composite where the interface itself is not modeled with finite elements. So we distinguish between the different materials at each integration point. And this is sometimes referred to be as the Gauss point method. Yeah, and this method has the advantage that it is easy to apply for an arbitrary cord and composite setup. Within our composite simulation, we model the cord as a continuum, and we use a transversely isotropic material model whose preferred direction is oriented to be coaxial to the filament at each integration point. So we model the twisted nature of the chords using inhomogeneously distributed preferred directions. And therefore, we need mainly two parts to solve our problem. The first one is we need an appropriate model of our chord geometry, and which contains or allows us to compute the filaments and the corresponding tangent vectors. And the second thing we need is we need a reliable representative volume element for uniaxial and cross-layer reinforced composites, which are able to consider shell loads like bending, for example. And the objective of this talk is to present you those both components and to compare the stiffness properties and the deformation of the resulting model for different chord approximations. So let's begin with our model of the twisted polymer chord. For a finite element analysis, we need, of course, a material model. And within this work, we use a very simple material model for a multi-filament yarn, which consists of two simple neo-Hookean hyperelastic models. The first one is an isotropic part, which represents a very soft matrix, for example, penetrated rubber of the chord. Yeah? And the second component is a very strong anisotropic component, which represents the filament. And the resulting material model is simply the parallel connection of both models. And as you can see, there are three material parameters in the model, and the filament orientation in the current configuration is represented by the structural tensor. And this tensor has to be provided by an appropriate chord model. To obtain a suitable model for the chord's geometry and especially the filament structure, we need a reliable simulation of the chord's twisting process. And I just start the simulation so you can see what we are going to do. We try to simulate the twisting process of the chord, and the initial configuration or the initial state of our model is we are looking at two parallel cylinders where the filaments are already twisted due to the yarn twist. So we have two cylinders of twisted yarns, and
how are you modeling the contact?
Frictionless contact or slight friction, Coulomb friction between the yarns. Okay. Okay, and this simulation sequence is as follows. In the first step, we apply a pre-stretch to the chord, and in the second step, we twist the chord to the target twist we want to simulate. And this is very close to the real manufacturing process of the chord. The boundary conditions of the model are applied by means of a nonlinear coupling equation, and this equation means, simplified, that all cross sections of this model, of the chord model, are similar. They just differ in the rotation about the chord axis and the translation along the chord axis. So if we know one cross section of the chord, we can reconstruct all cross sections of the chord. Yeah? This is expressed by this nonlinear coupling equation, and this is implemented in Abacus using its subroutine MPC. And this model has the favorable property that there are no surface effects, so it is sufficient to simulate only a few number of element layers in order to reproduce a correct contact condition, and therefore the model is very efficient. And as we can see in this picture, the flattening of the chord is very natural, and if we compare this to the microscopic image, it seems to be in good accordance. So, now we have, or we hope that we have a model which predicts us the chord geometry as well as the filament structure. And now we need a mathematical model for the chord geometry and the filament structure for our representation within the composite analysis. So this is not the aim of our work, this is only a necessary step. And as a first step to obtain a mathematical model is to model the cross-section of the chord. And the basic idea of this analytical model is to imagine, okay, we assume or we introduce a convective or three convective coordinates r, phi, and z, and these three coordinates are equal to the cylindrical coordinate system at the initial state of our twisting process, which we simulated. And due to the twisting process, this coordinate system became a general curvilinear coordinate system. And as we can see in this picture, the geometry of the yarn cross-section is a periodic function of phi, which motivates a Fourier series approach for the circumferential direction. And for material lines in the radial direction, we use a simple power series approach. So the complete model for the cross-section reads as follows. The cross-section of the yarn is the sum of these terms. And here you can see the Fourier coefficients and power series terms. And the unknown coefficients of this model are highlighted red in this equation. And these unknown coefficients have to be identified by means of the finite element simulation of the twisting process. And therefore, we use, of course, our previously performed finite element analysis and solve a least squares problem with the differences of the finite element simulation and the predicted nodal positions of our cross-section model. To accomplish our chord model, we now have to rotate the cross-section about the chord axis and to translate it along the chord axis. So with this step, we can accomplish the cross-section model to the full chord model. And as you can see, this equation is very familiar to the nonlinear coupling equation we used at the twisting process, for the simulation of the twisting process. If we further express the angle phi according to the twisting process of the yarns, then we can compute the filaments. Every filament in the chord can now be computed and the corresponding tangent vectors to the filament. So now we want to compare our chord model we obtained to microscopic images. In these both pictures, you can see the outline of the computed cross-section, chord cross-section, compared to microscopic images, and you can see that this model matches very well to the cross-section we observe in experiments. At the right, we can see the computed filaments in comparison to the real filaments. And summarized, we can say that this model seems to be a suitable approach to reproduce the chord's geometry, including the filament structure. And I want to focus that these tangent vectors are the necessary input for our composite simulation. So let's proceed with the extended periodic boundary conditions. We want to analyze shell-like representative volume elements, which means that we have, for example, a uniaxial reinforced composites with two directions of periodicity. And we want to analyze stress distributions due to shell loads like tension in chord direction, lateral compression, shear loads, bending, torsion, and so on. And the principal idea of the extended periodic boundary conditions is that we introduce for each direction of periodicity a master and a slave surface, and we demand that for every material line element at the master surface exists the identical but rotated material line element at the slave surface. This leads us to the following constraint. This is the constraint I already mentioned, and we can see that the rotation between the master surface and the slave surface maps the material line element from the master surface to the slave surface. As consequence, the deformation gradient at the slave surface and at the master surface differs only in this independent rotation tensor. However, if we look at the right Cauchy-Green tensor, then we see that the right Cauchy-Green tensor is for both sides equal. So we don't recognize any rotation within this quantity. The normal vector gets rotated, of course, too. As we all know, or we want to consider a very simple material where the second polar Kirchhoff stress tensor is a function of the right Cauchy-Green tensor, the current right Cauchy-Green tensor, and of course its history. And because the right Cauchy-Green tensor is equal at the master and slave surface for all time points, the second polar Kirchhoff stress tensor is equal for the master and slave surface too. However, the stress state or the Cauchy stress tensor is rotated or differs in a rotation from the master and the slave surface. In this picture, for example, we can see a single curved plate and a Mises stress distribution. And what we can see is that there are no surface effects due to the boundary conditions. And furthermore, if we set the rotation tensor to the identity tensor, then we obtain the classical periodic boundary conditions, which is a very favorable property. How we realize this within the finite element method? Let's assume, or let's consider our meshed composite, and we introduce, or we choose one node of our composite to be as the basis node, which gets pinned in order to suppress the rigid body motion of the finite element model. Furthermore, we introduce for each direction of periodicity one pilot node which controls the deformation of the composite in the following. And now we define the material line elements at the slave surface with an arbitrary node J and the pilot node of the slave surface. And the material line element at the master surface is defined between the corresponding node J and the basis node. Here. So we obtain this constraint between our nodal points. We now have to control the rotation of the master surface and the relative rotation between the master and the slave surface, and this is achieved by a macroscopic curvature tensor. Furthermore, we can enforce or we can apply macroscopic membrane loads by means of such a macroscopic membrane tensor. So these were the kinematics of the model. Now we look at the kinetics, and therefore we look at the power balance of our model. And here you can see the power of the nodal forces within our model. And we demand that this is equal to the power of our macroscopic quantities. And if we use the relation between the nodal forces and the nodal velocities, we can obtain the stress resultant and the moment resultant tensor. So this model is able to determine the stiffness properties because we are able to compute the real stress resultant and moment tensor, and we only have to prescribe the macroscopic curvature and membrane tensor or stress resultant and moment tensor. And if we consider periodic structures with no Gaussian curvature, the solution is periodic as well, and therefore free of any surface effects. Unfortunately, if we have a Gaussian curvature, we suffer from surface effects, which is not very nice, but we cannot change it. Currently, the work is focused on combined bending and tensile loads, because therefore an external pressure load is required. So far to the model. Now briefly to the results. First, the uniaxial reinforced model we want to compare 3 different chord models. The first has a cylindrical shape and an isotropic neo-Hookean material model, and this is equal to a single monolithic filament. The second one has a cylindrical shape too, but in transversely isotropic material model, and the preferred directions are always coaxial to the chord axis. So this is equal to a bundle of parallel filaments. And the third model is equal to our new geometry model. And these both 2 models are the current state of the art within industries. We fit the parameters of the chord models to equalize the tensile stiffness in chord direction, and we model only a very small rubber layer to increase the impact of the chord model on our results. And we are interested in the different stiffness properties. This is a table with the material properties I identified, but this is not so interesting at this point. Let's look at the stiffness properties with respect to the composite, which is reinforced by our new model. We can see, compared to a pure rubber block, our model has a slightly increased stiffness in lateral direction, but a very strong reinforcement under shear, torsional and bending loads. However, an isotropic chord model shows a very increased 6,000 times higher lateral stiffness than our model. And the shear stiffness and torsional and bending stiffness is dramatically increased too. So such an isotropic chord behaves like a rigid body, for example. And if we consider the anisotropic chord, we can see that under lateral shear and torsional loads, there is no significant reinforcement. But if we consider the bending stiffness, we can see that the anisotropic model and the isotropic model has nearly the same bending stiffness. And this is a contradiction to our experience. Then we know that a real chord has not the same bending stiffness as a compact body. So those both models have deficiency in the stiffness properties. And our model is able to predict these in a realistic magnitude. And what is very important, none of these models is able to reproduce the tension twist coupling of the chord, which can be very significant in such analysis. Yeah, then I have furthermore for the cross-layer reinforcement, I will skip this. One interesting thing is, if we consider a cross-layer reinforced composite and perform a uniaxial tensile test, then this leads to a change of the angle between the chords. And this introduces a shear deformation to the chords. And as we can see, for the chord model with parallel filaments, for example, we don't see any warping and estimate a very low logarithmic strain. This is not realistic as we can imagine. At the right side, we can see the isotropic chord, and for the rubber matrix, the isotropic chord behaves like a rigid body and rotates. And this causes very high strains in the rubber matrix. And within our model, we observe an increased shear stiffness of the model, which is realistic, but if you look at the values of the logarithmic strain, you can see that this model underestimates the deformation, this model overestimates the deformation, our model is somewhere between, which seems to be realistic. Okay, let's summarize what I've told you. I presented our finite element based model of twisted polymer chords, including twisting simulation and analytical model. This seems to be a very suitable model. I presented you extended periodic boundary conditions to cover shell loads. And I presented you briefly some results to show you that our new model we proposed have realistic stiffness properties compared to the simplified models which are all currently used within industries. Okay? This is the core message of the presentation. Further development will be that we extend our model to hybrid chords. We want to model inelastic behavior of the filament material, finite element-based parameter identification, and so on. Then we made significant progress to combine tensile and bending loads. And of course, these Gauss point methods have some deficiencies near the interface of the materials, and we have to spend some effort in this case. For example, extended finite element method, the submodel technique, or physically based smoothing algorithms to improve our results near the interface. So then I'm at the end of my presentation, and I hope we have time for some questions. Thank you very much.
Very much. In fact, we have not much time for questions. Just one short question for the result.
On your slide number 9, there was an interesting constitutive equation. You have combined G3 and G3 minus 1.
Slide 9. Slide 9?
9.
Yeah.
Yeah. In the last equation, you have combined G3 and G3 minus 1.
Yeah.
Physical motivation for this combination.
No, this is just simply a linear volumetric part which only holds for slight volumetric deformations. So we hope, we have to check after the simulation if strong volumetric deformations occur. If this would be, then we have to change this term.
Okay. Let's send the speaker.